Good day. I am Ritisha and Krishna, and our theme is recursive systems. For our first chapter, we'll explore the concept of recursion. To gain a deeper understanding, we'll examine recursion through the lens of crystallization and the physical experiments conducted to study it. The principle of recursion states that it is a self-similar process where the output becomes the input for the next iteration. Recursion is commonly observed in crystallization processes. Crystals are formed through an ordered arrangement of particles due to Brownian motion, explained by the diffusion-limited aggregation (DLA) process. According to DLA, particles undergo a random walk, influenced by diffusion, where they spread out due to thermal energy. As each particle attaches to the aggregate, it creates branches that are self-repeating, forming a fractal. The characteristics of crystallization include self-similarity, nucleation, purity, and concentration. The growth and branching of crystals are based on a recursive system, where each new arrangement is similar to the previous one. For instance, mirror symmetry can be observed after every 3 cells, or a simple repetition pattern. The formation of crystals is highly dependent on the impurities present. An impurity attracts particles, initiating the nucleation process, which in turn starts the aggregate formation. This attracts more particles arranged in the same manner, leading to fractal growth with self-similarity at every scale. To understand the formation and growth of crystals, we conducted an experiment using sodium acetate. We followed these steps. Particles were attracted to the skewer, branching out and initiating a chain reaction, creating dendrites throughout the beaker. In another experiment with monoammonium phosphate, we observed a different crystal geometry. These crystals, formed over 55 hours, appeared more elongated, solid, and tetragonal in shape. The crystals on the left formed at the beaker's base, while those on the top right formed on pieces of rope. These crystals developed on a support, making them sturdier. To further explore filament-based formation, we conducted an experiment with borax, using different filament arrangements to observe growth patterns. This experiment resulted in the formation of cuboidal crystals layered on top of each other. The variation in crystal formation is due to differences in solution purity. The observed pattern involves crystals attaching to each other, creating large aggregates and resulting in the visible tetragonal and cuboidal crystals. After the physical experiments, we attempted to simulate these processes digitally using the diffusion-limited aggregation concept. The concept involves a random particle approaching the center, attaching to the closest point, and creating a branch. This iterative process is repeated 200 to 300 times to generate different results. A similar experiment was conducted in a 3D environment to simulate the growth of an aggregate on a filament. The parameters varied here included the number of point attractors, branch length, and number of iterations. We digitally simulated the borax experiment using the same filament form. Next, we conducted the same simulation with an increased number of lines, resulting in higher resolution. Through these experiments, we observed the formation of aggregations and crystal growth on a thin filament. This interplay between mass and void became the subject of further study and experimentation. After understanding the behavior of aggregation, we aim to produce similar results on a larger scale using materials with properties akin to aggregate growth. We also endeavored to develop a theory on the production system. Materials exhibiting such behavior include expandable foam, hydrogel, and self-healing concrete. We chose readily available and easy-to-use expandable PU foam. Polyurethane foam, commonly used for thermal insulation, expands upon contact with air. It is produced by mixing 2 liquids, polyols and isocyanates. The ratio of these liquids determines the final free-rise density and rigidity of the foam. This foam typically doubles in size in a humid environment. We created forms using pipe cleaners and jute threads, then sprayed the foam onto them, causing them to expand and add mass to the thin filament. Starting with a catenary form, we suspended it from a support and sprayed PU foam. Once removed, the solidified foam allowed the forms to stand independently. We began with simple 3-point suspensions and gradually increased complexity to achieve more mass and voids. However, due to damaged material, the experiment yielded unexpected results. Taking inspiration from the physical experiment's behavior, we digitally simulated 2 aspects, thread behavior generation and aggregate growth on the threads. Following our exploration of linear forms, we simulated a cuboidal form to understand the spatial qualities suggested by the observed behavior. After these digital explorations, we physically recreated these forms as well. Through these experiments, We realized that these forms have the potential for spatial quality. Some more iterations. After the initial experiment, we digitally simulated the material's behavior and its interaction with the filament. The logic here is that a geometry is described, and a set of anchor points is decided. Using these, a path for the filament is created. Growth starts at random points, accumulating and growing further to result in behavior similar to that seen in physical experiments. Starting from simple vertical weaving of the filament and increasing complexity, we understand how aggregation happens on each form. Using the initial digital exploration as a base, we tried the next set of experiments with linear forms to understand the extent to which they can stabilize themselves without support. We inferred from these that the more layers applied to the filament, the sturdier it is. However, this reduces the negative space inside the structure. These were further explorations and changes in the complexity of the filament. By combining linear and cuboidal forms, adding a single cuboid, then two, and so on, these result in forms with greater depth. These forms expand in volume in all directions by combining geometries like cylinders and cubes. We also visited a factory to understand how foam production takes place at a much larger scale. There are 3 methods of production: machine pouring, hand mixing, and portable can. Essentially, all these methods use the same 2 liquids but at different proportions. In the machine system, the liquids pass through a chiller and are poured or sprayed at high pressure to mix the liquids properly and give rise to the foam. The hand mixing method churns the polyols and isocyanates using a blender and then pours them into a mold. For the production system, a drone was the most feasible option. The idea is to use a drone to weave a filament at a larger scale on which the foam would be sprayed. The drone can access places that humans cannot and can result in intricate filament forms. We refer to ETH Zurich's experiment with drone weaving. The researchers have developed a drone that can create complex wire structures in mid-air, similar to how a spider builds its web. The drone is spider-like and can weave high-rise structures out of cable. Each quadcopter drone is equipped with a spool of strong plastic cable that runs out behind it as it flies. One end of the cable can be secured by making several turns around a pole. The drones are positioned and directed autonomously from the ground by a central computer. For example, to loop cables around each other, the computer directs 2 drones to fly through certain points at an exact time. In this way, the fleet can tie complicated knots and form large, regularly repeating patterns strung between fixed structures. We developed a scenario as an attempt to understand the possible real-life applications of this suspended lightweight system prototype. Taking context of PALs, which are tight and dense urban areas with limited ground space, the idea is to create a prototype that expands both vertically and laterally within tight gaps, employing lightweight materials. In this chapter we create digital and physical prototype based on our scenario. To simulate the idea of building between 2 facades, we ran the same code between 2 planes. Slowly we increased the number of facades with variable alignment to increase complexity and get closer to real urban fabric. Here we built a scaled prototype of the digital model, physically. Over the woven thread, polyurethane foam was sprayed to simulate the aggregation process on a larger scale. As the mass aggregates, we begin to observe volumes and potential spaces forming within the model. Here we observe the application methods of PU foam. Further we simulated the scaled-up model digitally as a prototype. Here we attempted to put the built in the proper context. Here, we look at the proportions for the proposed prototype. Chapter 5. Way Forward. The design system of using drones to weave a network of ropes in a recursive choreography is used here. The experiment here shows how a drone would move throughout the numbered points. We have used only one hand to simulate the real-life situation. Increasing complexity of weaving pattern. To understand how a drone would carry rope, we experiment with a customized drone and attempted to move from one point to another. This was our departing point where we took the designing system of suspension and interpreted its application in different contexts. Taking forward the approach of a suspended lightweight production system, Ridisha have explored and proposed a meditation center on a seaside cliff. The adaptive production system can be used to construct in challenging terrain where it's not possible for construction material or even direct human access. The idea here is to not dig and damage the terrain but suspend over it and eliminate heavy construction materials and processes. There are 2 types of arrangement possible while weaving from cliffs. One is the direct connection where the drone takes the cable from one point to another. This is the base cable. The other way is the indirect method where a set geometry can be made on support, which would otherwise be difficult to make on site. This geometry would be carried to and attached to the base cable and pulled from other anchors. For simulations, I first define my geometry and anchor points on it. Then develop the hanging ropes or curves over it. Starting from a simple cube, I increase the complexity of geometry. Upon running the aggregation simulation, different kinds of volumes and spaces were observed, ranging from simple bridge-like pathways to much more complicated volumes where different spaces interacted with each other. Now, the sight of a seaside cliff, for example, offers a specific experience where the vast horizon instills a feeling of stillness and presence of mind. The dynamic waves create a natural rhythm, calming oneself. The soothing sounds and isolation offer tranquility, and the experience of levitating above the chaotic and calming waves is peaceful. So, the program suitable for the site was a meditation center where one can be free and away from the city noise. The center includes a meditation hall, a yoga deck, a combination of open platforms, and personal meditation pods. For the first iteration, the structure is below the cliffs and not directly visible at eye level as it has to be part of the context. Once one descends from the entrance, they actually see the size of the structure. Here, it tries to cover the maximum area, but there aren't multiple levels and volumes generated. Here, I have explored more levels, considering where all the spaces can be allocated and what the overall scale of the project should be. The idea here is to funnel visitors towards the cliff edge, leading them down to the main spaces. More programmatic iterations. In the next iteration, I broke it into 2 parts, with one being the connecting section from one cliff to the other. Part A of the plan shows a clearer sense of volumes and space for meditation halls and personal pods. In Part B, I have tried to accommodate viewing decks, personal meditation pods, and even a common hall in the bridge, while maintaining a straightforward circulation pattern. For the final design, I have combined aspects from all the previous iterations. The predefined geometry has specific openings allowing for view and circulation. Rope generation based on geometries. This will be executed on site using drones. The site plan demonstrates how the structure fits into the topography, connecting one cliff to another. As visitors descend, they arrive at the viewing deck and then get closer to the sea. The connected yoga and meditation areas offer clear views of the sea and cliff without visual disturbance. The non-linear connection follows the curves of the rope, allowing one to experience the entire space in a unique way. Section BB. Suspension of ropes and lightweight solidification can be used to build in inaccessible areas without digging and damaging the terrain. This production system gave me the opportunity to experiment with a meditation center and design a holistic, levitating approach. For my project, Krishna have built aerial structures. Site: Times Square. The abundance of people on the ground level presents opportunities to expand further upwards. Roof plan. The organization is based on the idea of connecting the facades, placed over the crossroads. Isometric view. The central core connects to facades via arm extensions. The overall porous texture allows for permeability. Plan. Level variations along the floor plane create interesting spatial interactions. Section. The variable floor plane allows for varied interactions within the space. Each arm is distinct from the others. Section. The arms also open up to the environment at various points, again facilitating permeability. Section. The building's connection to the facade bulges for structural stability, and also functions as a lobby before entering.